today of introducing a colleague of mine I've had the privilege of working with. This is Professor Gabriel Orebi Gann in the physics department here. She did her Bachelor's of Arts and Master's of Science at the University of Cambridge, and did her doctorate in particle physics at Oxford. And you were a postdoc at the University of Pennsylvania with Josh Klein, who I serve with on HECOP right now, and came to the Berkeley faculty in 2012. And she's going to tell us today about her research in neutrinos and the big picture. And I think it's very interesting. When I was at Livermore, one of our great acquisitions there was a fellow by Adam Bernstein. Many of you know him. We actually have students here who work with Adam Bernstein, who was one of the pioneers of what's called, believe it or not, try not to crack a smile, applied antineutrino physics. This is a particle that took 25 years to discover and has a cross-section so small that low-energy neutrinos will go many light years of lead before interacting, and yet is being contemplated as a tool for the monitoring of nuclear reactors. And in fact, I think very interesting headway is being made. And Gabriel and I have been co-PIs on a grant from the NA22 organization and through the NNSC in carrying out this R&D that the NNSA is interested to see the university pursue. So without further ado, I'm going to turn it over to Professor Orebi Gann. Here be dragons, mysteries of the neutrino.
Thank you for the introduction, and thank you for the invitation to be here. One of the shorter journeys I've had, to give a colloquium, across the road. So you may be wondering about my title, Here be dragons. Here be dragons is a phrase that was used by ancient cartographers to denote dangerous or unexplored territory. So it's always seemed to me a fairly apt description for the field of neutrino physics. So to give you an overview of what's to come, we're going to take something of a journey through history. We'll start with discovery of the neutrino. We'll move into the first observation of neutrino oscillations. Then we'll come to the present era, what I call the precision era of neutrinos, and some of the open questions. And finally, we'll look to the future and what the next generation projects might be able to address. Now, at the same time as a journey through history, we'll also take something of a journey through technology, starting with water-Cherenkov detectors, which were critical in the first observation of oscillations, moving on to today's liquid scintillator detectors, and then discussing some future novel technology. So to begin, it's 1930, and Pauli is scratching his head because the process of beta decay has been observed, and the outgoing electron has a continuous energy spectrum. And that makes it difficult to conserve both momentum and energy simultaneously. So Pauli did something brave. He postulated a new particle, the neutrino, which he said would be massless, hence it can carry any fraction of the energy of the decay, and incredibly weakly interacting, which is why it hadn't previously been detected. Now, brave enough to postulate this new particle, he wasn't actually brave enough to do it in person. He sent a now somewhat infamous letter to a conference that begins, "Dear radioactive ladies and gentlemen, I have done a terrible thing. I have postulated a particle that cannot be detected." Fortunately, Pauli was wrong, but it did take almost 20 years before the first detection of the neutrino. And it was actually the antiparticle partner, the antineutrino, that was detected via the inverse of beta decay, so bombarding a proton target with antineutrinos, producing a positron, which annihilates in the target, and a neutron, which will capture after some delay. So this is a very nice coincidence signal, which significantly reduces potential backgrounds. And this experiment was performed in 1956 by Rines and Cowan here in the US at the Savannah River nuclear reactor. So we'll now skip a few decades. Convinced by the existence of these particles, we'd like to fit them into the standard model of particle physics. So, as we now understand it, matter is made up of fermions, which are organized into 3 generations. And they're divided into quarks, which are charged, and they also carry color, so they interact by the strong force, and the massive leptons, which don't carry color, so they interact electromagnetically or weakly. You also have the force carriers, which are the particles that mediate the forces by which the other particles interact, and of course the Higgs boson, which we now know gives mass to the fundamental particles. So there's a clear spot for the neutrinos. They fit in here. In the standard model, they're neutral, so they only interact weakly. They were massless. Remember, Pauli said they had 0 mass. And one might hope there are 3 flavors, one to partner each of the charged leptons. And in fact, a message popped up on my screen. Sorry. If we look at data on the width of the Z boson from the LEP experiment, you can see here the prediction for 2, 3, and 4 flavors of neutrinos, and the data agrees very nicely with the prediction for 3. Now this has the caveat that this is only sensitive to neutrinos that couple to the Z boson, so active neutrinos, with masses less than half the Z. So these 3 flavors of neutrinos have now all been detected. They're produced in a number of different ways. What we're going to focus on to begin with is the electron neutrinos that are produced in the sun. So this image should be familiar. This is the sun imaged in the electromagnetic spectrum. This is the sun imaged in neutrinos. So as the standard solar model tells us, and as we now understand, the sun is powered by nuclear fusion reactions. So there's protons fusing into helium, and that releases a lot of energy. That's the heat and the light that we see, and also a large number of neutrinos. So the field of solar neutrinos was initially conceived in order to use those neutrinos to better understand the sun, to test our understanding of those fusion processes. Of course, life is never quite that simple. The first experiments that turned on saw a significant deficit of the number of electron neutrinos expected. So this shows, as a function of the standard solar model, the SSM prediction, so black is the model predictions as a function of energy, the different experimental results. So you can see a number of different experiments seeing a discrepancy of between a factor of 2 and 3 from the theoretical prediction. And this discrepancy persisted for several decades. This is what became known as the solar neutrino problem. And there was a lot of discussion about what might be the answer. Some people said maybe the theory is wrong. But actually the standard solar model predictions for the speed of sound agreed incredibly well with helioseismological observations. So that seemed to give us confidence we understood what was going on in the sun. So then you start to question the experiments, and maybe there's something wrong with neutrinos. Of course, perception of this problem differed. There's a quote here from a paper in 1990 that says, "Most likely the solar neutrino problem has nothing to do with particle physics. It's a great triumph that astrophysicists can predict the flux of solar neutrinos to within a factor of 2 or 3. So some people looked at this figure and gave themselves a pat on the back and said, we got it right. So, of course, as we now know, this was one of the first indications of neutrino oscillation. So moving into the first observation, let me introduce the water Cherenkov detectors, which were critical in this observation. So the Cherenkov process is when a charged particle traverses a dielectric at faster than the speed of light in that medium, and what happens is light is emitted with a cone-like topology. It's sort of like a sonic boom in light. So you get this cone of light, which if you detect on a surface of photon detectors will appear as a ring. So what's nice about this is it retains directional information. You can trace back to see where your incident particle came from. And one of the most famous water Cherenkov detectors is the Super Kamiokande detector. This is a 50 kiloton detector. It's a vast amount of water surrounded by about 11,000 photon detectors. Each of these is a photon detector. There's a boat with people inside the detector. Just gives you an idea of the scale. And Super K detected solar neutrinos by the elastic scattering interaction. So a neutrino comes in, scatters an electron, and that electron produces Cherenkov light. So this is nice because you can point back to the sun. You can be really confident that you're actually seeing neutrinos from the sun. However, the ES interaction is sensitive primarily to electron flavor, but with some sensitivity to the other flavors. So the other experiment was the Sudbury Neutrino Observatory, or SNO, which is smaller. It's a 1 kiloton vessel, and instead of light water, it used heavy water. And the critical thing about heavy water is it opened up a couple of new interactions. So you can have the charge current interaction, where an electron neutrino interacts with a neutron in the deuteron, and this is sensitive only to the electron flavor at these energies. And then there's the neutral current interaction, where a neutrino just comes in and breaks up the deuteron, and this is sensitive equally to all flavors. So you have a measurement of the pure electron neutrino flux, and you have a measurement of the total flux independent of flavor. So this was our picture of the solar neutrino problem. The SNO results resolve this unambiguously. The charge current measurement, remember the pure electron neutrino flux, was suppressed by this factor of 3, as had been seen before, and the neutral current measurement, which remember is the total flux of neutrinos independent of flavor, was in beautiful agreement with theoretical prediction. So that confirms that we do understand what's going on in the sun. The standard solar model was right, but what's happening is the electron neutrinos produced in the sun are changing flavor before we detect them on the Earth. So this was big news. This hit all the headlines: Philadelphia Inquirer, Washington Post, New York Times, because this was one of the first indications of neutrino oscillation. Now, the idea of neutrino oscillation is that neutrinos are produced in their weak states, the electron, muon, and tau, but they actually propagate in a mass eigenstate, which is a different state. And physicists, being as creative as we are, those are called 1, 2, and 3. And you can view this as entirely analogous to classical coupled oscillators. So if you start a neutrino in, say, the electron state, call it the green one, there's a coupling to the other state, and over time, the motion, in this case, transfers to the other state. If you start it in what's called a normal mode, so for the coupled pendulum, you just start the two pendula together, then it'll stay in that mode forever. So that's equivalent to starting your neutrino in one of the mass states. So this is actually really exciting, because this is quantum oscillations. This is a quantum mechanical effect, but observed on a macroscopic scale. This is something we observe over hundreds of kilometers, or more if you're looking at the distance to the sun. So mathematically, you can think of this as a rotation of your basis. So this is in the simplified two-flavor scenario. You can view this as a rotation, and what that means is your new E state, for example, is some linear superposition of the new 1 and the new 2. So if you start your neutrino as an electron neutrino, it's some fraction nu 1, some fraction nu 2. Those propagate at different speeds, so at some time later, it'll be a different superposition with some probability of looking more like a muon neutrino. And if you just express this as a simple rotation, you can find a probability for that flavor change, which depends on the mixing angle, just this rotation angle. It depends on the distance that the neutrino has propagated and its energy, and critically, it depends on this delta m squared term, which is the difference of the squared masses. So observation of neutrino oscillation requires non-zero neutrino mass. That's really one of the critical points. So the smoking gun was actually observation of the oscillation pattern. So you can see here this survival probability as a function of L over E, and you can see the oscillation very clearly from the Canland reactor experiment. So Canland was looking at antineutrinos produced in a reactor. And this has got a lot of press recently. So the 2015 Nobel-Prize in Physics went jointly to the directors of SNO and Super-K for the discovery of neutrino oscillation, which shows that neutrinos have mass. So again, this is one of the really critical points. So let me summarize our current understanding of neutrino mixing. We know that we have these three flavor states, which are actually linear combinations of the three mass states. And we know, actually from solar neutrinos, that the nu 2 state is heavier than nu 1. But we don't know whether nu 3 is the heaviest state or the lightest. So that gives us two options for the so-called mass hierarchy, the ordering of the mass states. The mixing itself is defined with three mixing angles, two mass differences, and a phase term. And you can express that this way, splitting it up into the three sectors for each of the three angles. And so the atmospheric mixing angle has been well measured by experiments like Super-K and Minos. The short baseline reactor sector is well measured by experiments like Diabay and Reno. And then you've got the solar angle measured by Snow and Camat. So I mentioned a phase term. That appears here. This phase term, if this is non-zero, then it tells us that neutrinos and antineutrinos actually can behave differently. So for putting together this complete picture of neutrino mixing, 5 experiments were actually jointly awarded the 2016 Breakthrough Prize in Fundamental Physics. So that's a fairly complete picture of neutrino mixing. You might ask, okay, what's left? What do we still need to understand? So that brings us to the current era and motivations for continuing to study neutrinos. So one reason is that the weak interactions means neutrinos actually are a unique probe of places we otherwise wouldn't be able to see. So for example, we can use them to actually see into the core of the Earth, inside the sun, and even far distant supernovae. And then also it is a fascinating particle in its own right, and there are properties that we still don't understand. We don't know the ordering of the neutrino mass states, whether it's normal or inverted. We don't actually know the absolute neutrino mass scale. I mentioned the possibility of entropy violation. We don't know if that's there or not. And perhaps the most fundamental question is the very nature of the neutrino. The neutrino is the only known fundamental fermion with the potential to be its own antiparticle, or what we call a Majorana neutrino. And this, some of you may have noticed my title slide had an Escher picture on it. This is where that comes from, because for me this is sort of reminiscent of some of Escher's tessellations, where the blue birds going to the left form the negative space for the white birds going to the right. So if neutrinos are Majorana, then this could actually explain the origin of our matter-dominated universe. That's a somewhat grandiose statement, so let me explain. And in order to do so, let me just give a brief description of what I mean by Majorana neutrinos. So as a reminder, a particle's helicity is simply the projection of its momentum onto its spin. So if the two vectors are parallel, then it's right-handed. And in the massless limit, helicity and chirality are the same, so neutrinos will all be left-handed. However, if the mass is greater than 0, you can always boost to a frame in which the helicity will flip, because the momentum seems to be going the other way. So the discovery of non-zero neutrino mass tells us that you can have a right-handed neutrino. And Majorana neutrinos, the idea is actually very simple. For Majorana neutrinos, the antineutrino is simply the opposite helicity state. So what implications does that have? Well, if neutrinos are Majorana, that makes them different from all the other fundamental fermions. So maybe life is simpler if they're Dirac. That means everything behaves in the same way. However, if neutrinos are Dirac, then we have no way of explaining the absolute neutrino mass scale. Neutrino masses are many orders of magnitude lower than the other fundamental fermions. It also means we need to introduce some new fundamental symmetry, or promote lepton number to a fundamental symmetry. It means there is some difference between matter and antimatter beyond simply electric charge. So that sounds a little bit challenging. Maybe life is simpler if neutrinos are Majorana. We don't need a new conservation law in that case. And maybe the strongest argument I've heard from theorists is that neutrinos are Majorana because they can be. Which is actually a little more than it sounds. There is nothing to prevent it, so it must be possible. However, if neutrinos are Majorana, you cannot explain neutrino mass by the standard Yukawa coupling to the Higgs. The simplest mass term is 5-dimensional, and that's not renormalizable. So that suggests it's probably not the most fundamental theory. So either you need a new mass mechanism, or you can possibly explain it with a triplet of Higgs particles. So either way, this is a major open question, and in some sense there really is no standard model until we understand how neutrinos acquire mass. So this is a major fork in the road. For me, so I don't know how you feel looking at this looks like the exciting path, the challenging path, this is new. So for me this is Majorana neutrinos, it means new physics. It means some kind of new mass mechanism. And it would just be kind of fun if, having got so excited about the Higgs, it turned out that's not all there is. So this one looks like the easier path, but actually you don't know what's just around that corner. And if it turns out neutrinos are Dirac, you still need new physics, because you need some kind of new symmetry to help explain the difference between matter and antimatter. So no matter what, it's exciting either way. Now I said that Majorana neutrinos could explain the origin of our universe. Let me go into that in a bit more detail. So CP violation, which I mentioned, is a difference in the behavior of matter and antimatter. So if neutrinos exhibit CP violation, then the rates for these two processes would be different. Now, almost every interaction we know about conserves CP. That means matter and antimatter are made and destroyed in equal amounts. There is a small amount of CP violation in the quark sector, but it's very small. So we would therefore have expected the Big Bang to behave in the same way. The universe should have been created with equal amounts of matter and antimatter. However, if you look at the universe, that's not true. From what we can see, there is a vastly greater quantity of matter than antimatter. And that's a good thing for us, because if you bring matter and antimatter together, we all know what happens. And if the universe were created in equal amounts, you might imagine the entire thing would have self-annihilated by now. So we need, according to our understanding, there must be some amount of CP violation in order to explain this asymmetry. And the amount we've seen in the quark sector is not sufficient. So we look for it in the lepton sector. And how do Majorana neutrinos help us? Well, if neutrinos are Majorana, they can undergo something called the Seesaw mechanism. What that is when you introduce a large Majorana mass into the standard model Lagrangian, you split your standard Dirac neutrino into two. You get a very, very light neutrino, and that's the one that we've observed in terrestrial experiments, and that would explain the very light neutrino mass bonus. And then you get this very heavy sister particle, which would have been created in the Big Bang. And if this particle undergoes CP violation and lepton number violation in its decay, that could give us the current asymmetry. So Majorana neutrinos potentially hold the key, and it's a very active field searching for these particles. So how does one do it? Well, we come back to beta decay, the process that led us to the discovery of neutrinos in the first place. For a small number of isotopes in nature, beta decay is actually energetically disfavored, and they can decay via something called 2-neutrino double beta decay, where it's exactly what it sounds like. You basically have two neutrons undergoing beta decay simultaneously, so you get 2 electrons and 2 neutrinos. Now, if the neutrino is its own antiparticle, they can effectively annihilate inside the nucleus, and the only thing that escapes is the electron pair. So if we can observe this neutrinoless double beta decay process, that tells us neutrinos must be Majorana. Now the limits on the half-life of this process are very long, 10 to the 25 years. For comparison, the age of the universe is 10 to the 10 years, so it's quite a long time. But fortunately, Avogadro's number is very large, so you do actually have some hope of seeing this process when you look at the molecular atomic level. So if you observe neutrinoless double beta decay, that tells you that lepton number violation occurs. This violates lepton number by 2. It tells you neutrinos must have some Majorana nature. And as a bonus, the rate of this process actually is sensitive to the neutrino mass. So the signature for this process looks like this. The energy spectrum in the summed energy of the 2 electrons is a continuous spectrum similar to that for beta decay. And in the case of no neutrinos, you get a peak at the endpoint for the same reason, that now the electrons have to carry the entire Q value of the decay. The rate depends on 3 factors. There's a phase space factor, which can be calculated. There's a nuclear matrix element, which is much harder to calculate. And if you look at different models, so this is different isotopes, and this is the nuclear matrix element, the different colors are different model predictions. So you can see there's a large variation by factors of 2 or 3 in this calculation. And then there's the effective Majorana neutrino mass. And this is where you get some sensitivity to the absolute mass and to the mass hierarchy. So this mass is a linear combination of the masses of the 3 mass states. And you see that the M3 is modulated by the sine squared theta 1,3 term. Theta 1,3 is by far the smallest of the 3 mixing angles. So in the case of the normal hierarchy, you have the smallest contribution from the largest neutrino mass. So that means that the phase space for this process looks like this, where this is the Majorana neutrino mass, and this is the lightest neutrino mass. And it splits into these two different regions for the two different hierarchies. So this is a very challenging process to observe because of the very long half-life. You're looking for a very small number of events. And the signature that I showed earlier was exaggerated. In reality, you're looking for a tiny little bump here. So you need a very large mass detector to increase your signal statistics. You need ultra-low background, which means you need to be deep underground. You need ways to purify every material in your detector. And ideally, you need ways to discriminate background events in situ, in your detector. You need good energy resolution to prevent this background from just smearing out your signal. And ideally, you'd like to be able to interchange isotopes in a single detector in order to verify a signal. And it would be very nice to have tracking capability to start understanding the mechanism for this process. So this is a very active field. There really has been an explosion of technology. And I'm not going to go through them all in detail. The take-home message from this slide is that different approaches have different benefits and different limitations. So these are the 5 sort of major considerations for these experiments. If you want to achieve a very large target mass, really the best way to do that is with the large-scale scintillator detectors. If you want ultra-low background, then you do best with a liquid target because it's easier to purify liquid than a solid. But if you want really good energy resolution, you really want either germanium detectors or high-resolution bolorimetry. The solid-state detectors are really incomparable for their energy resolution. If you want to be able to exchange isotopes, then either these tracking detectors, which use foil targets that you can just change out, or the large-scale scintillator detector. And if you want tracking capabilities, then you need a tracking detector. So you can see that the advantages are spread between a number of different technologies. So the one that I'm going to focus on is the large-scale liquid scintillator technology. So let me just introduce the idea of scintillation detectors. What happens is a neutrino comes in, it scatters an electron, that excites states in the scintillator, and they emit photons on relaxation. And that light is emitted isotropically, and you get about 50 times as much as you get for Cherenkov light in the standard scintillators that we use. You do sometimes need a FLUR, a wavelength shifter, to shift those photons to a regime that's optimal for propagation and detection. So the experiment I'll focus on is the successor to SNO. SNO stopped taking data in 2006, and the detector became available. So at that point, along came SNO Plus. So we are reusing the original detector, but replacing the heavy water target with liquid scintillator. SNO Plus is located in the SNO lab facility, which has been built up around the original SNO cabin. So here is SNO, which is now SNO Plus. Originally, this was the lab. All of this is new, and this is a potential future extension. So this is a view of the mine where SNO lab is located. This is shaft number 9, where you go underground. So if you're going underground to the lab, you get dressed in the full mining gear. You queue up for the cage, which is basically a big metal box, that then goes 6,800 feet down this shaft to bring you out in the mining tunnels below. When you get down there, you then hike about 2 kilometers through active mining tunnels. So they're dark, they're dirty, often it's about a foot or 2 deep in water, until suddenly there's a light at the end of the tunnel, and that's SNO lab, so this is the entrance to SNO lab. And when you get there, all the mining gear has to come off, because SNO lab is a clean room environment, so you go through a set of showers, you get to put on a very swanky set of nylon overalls, and you emerge into something that looks like a scene out of a 60s sci-fi film. So everything is white plastic. So I mentioned SNO lab has been expanded, and there are a number of other experiments. This is just a couple of shots of a dark matter experiment that I work on being deployed. And this is a couple of my group members running shift and then on their way back up after a long day underground. So you can see it's very exciting working underground. So SNO Plus has a very broad physics program. The primary goal is a search for neutrinoless double beta decay, But there's also a wealth of other physics, including the ability to detect neutrinos from reactors. Geoneutrinos, neutrinos produced inside the Earth. This allows us to understand models for heat production inside the Earth. We will be continuously live to potential supernova. We can do sensitive searches to certain modes of nucleon decay, and we can actually address a number of open questions in solar neutrinos. But for now, I will focus on the double beta decay search. So I showed a lot of different technologies for this physics. What are the advantages of the liquid scintillator approach? Well, one of the primary advantages is the ultra-low background. Our backgrounds are actually dominated by the boron-8 solar neutrinos. You can't turn off the sun. But fortunately, SNO measured those with incredibly good accuracy. So the reason it's such low background, one reason is that we can fiducialize. What does that mean? Well, here's a photo of the detector. So you can see this is the acrylic vessel. We filled that with liquid scintillator, which will be loaded with tellurium, our target isotope. That allows us to do the double beta search. And by fiducialization, I mean that we just define a fiducial volume inside the acrylic vessel, and that reduces backgrounds from all of the external regions. So we have all of this scintillator as an additional buffer region. So that keeps the backgrounds very low. We can also identify backgrounds in situ because the scintillation time profile looks very different for alphas and betas, as you can see here. So you can distinguish different particle types, and you can reject radioactive backgrounds by the coincidence of their decays. It's also a very deep location. The 6,000 meters water equivalent means cosmogenic backgrounds are almost negligible. Other advantages include a very high detection efficiency and the ability to do what I call a source-in, source-out calibration. So we can measure all of our dominant backgrounds before we put the tellurium in the detector and introduce any potential signal. So you can almost do a subtraction analysis. The other main advantage is the potential to go to incredibly large target masses. If you want to move to a next generation project, you just need to load more tellurium into your existing detector. You don't need to build an entirely new detector. And of course, a bonus is the broad program of additional physics topics, which I already mentioned. So why did we choose tellurium for our target isotope? One of the reasons is that of all of the isotopes, it has the highest natural abundance, which means that you can get very high loading without needing enrichment. Enrichment is a very expensive process. It has a favorable ratio of nuclear matrix elements for the 2 neutrino and 0 neutrino process, which makes us less sensitive to the fact our energy resolution is not as good as the solid state detectors. It keeps that 2 neutrino background down. At the particular Q value, which is about 2.6 MeV, we can reject the relevant radioactive backgrounds with incredibly high confidence, which again keeps our backgrounds low. And critically for us, we can load it into organic liquid scintillator with good optical properties. So this is what SNOPLUS would see with 5 years worth of data. This is with 0.5% loading of tellurium in the scintillator. You can see the red is the potential signal peak. This is sort of at the limit of current experiments. This is the 2 neutrino background, and the various colors of radioactive backgrounds. This brown one, this flat one, is the boron-8 solar neutrinos. So what we actually do, in part to combat our limited energy resolution, we define an asymmetric region of interest, and that keeps the background from that 2 neutrino very low. And in this ROI, our dominant background is actually the boron-8 solar neutrinos. So let me just summarize the status of SNOPLUS. We've completed installation of a rope net. This is necessary to hold the detector in place. We have a light water buffer region around the detector. So once we fill with liquid scintillator, which is less dense than water, without the rope net, the vessel bobs upwards. We've completed extensive cleaning of the entire cavity, including the acrylic vessel itself. So this is a ladder deployed inside the acrylic vessel, and collaborators actually went inside and scrubbed it by hand. So I call this the superheroes of SNOPLUS because this was quite an impressive job. And here, so this is one of my collaborators inside the acrylic vessel, which is so clean that it almost looks like he's flying. And this is another collaborator scrubbing the vessel by hand, you can see. He's actually on the outside of the vessel. You're looking down from the neck. He's on the outside, supported by ropes, pretty much at the equator. So this is reminiscent of the last. We've completed upgrades to the electronics in order to handle the higher data rates that we expect in the scintillator detector. And we are currently in the process of filling with water. So this is a photograph from our camera systems that are installed at the radius of the PMTs. You can see the water level here. Actually, at the moment, we're up to about here. So we're much higher. In a few weeks' time, we will reach the equator. And then a little while ago, we had a fairly illustrious visitor. Stephen Hawking actually went underground when the original SNO results came out. And when SNO Lab was expanded, he wanted to see the new facility. So he came underground, he met a lot of the scientists. This is Mark Chen, this is director of SNO Plus. Here's Art, the director of SNO, recent Nobel laureate. And I think at this moment, the photographer had a spark of genius because he took this photograph, which is reminiscent of another professor. So the plan for SNO Plus, as I mentioned, we are filling with water as we speak, and we will have data from that this summer. We will fill with Scintillator towards the end of this year, and then we will load with Isotope in 2017. So from here onwards, the plan is to be determined, and it'll depend on what we see with the Isotope Loaded Scintillator and the state of the field as to whether we continue with the double beta decay or we switch back to an extensive solar neutrino study. So how does the sensitivity compare to other projects? So current limits sit about 150 to 400 millieV. And if we look at future projections, the Majorana demonstrator will come close to this inverted hierarchy region. The Quarry experiment, this is a bolometric experiment, will just start to move into this region. And SNO Plus with 0.5% tellurium has about a factor of 2 better sensitivity. So a highly competitive result. But of course, the big question is how do we go further? How do we improve this sensitivity even into the normal hierarchy region? So the 0.5% run in SNO Plus is intended to be a prototype for a multi-ton experiment. And there is active R&D into the metal loading to increase the light yield and to reduce the correlation with optics, so you could load more without losing light. And you can see we've successfully loaded 5%. Actually, we've now successfully loaded 15%, although it does quench the light, so there's ongoing R&D. The other upgrade path for us is really very straightforward. The photomultiplier tubes we have are still those from SNO. They have a peak efficiency of 20% if you're lucky. And Hamamatsu now made ones with 34% efficiency, the same format. So we could just plug and play replace those. We also have these light concentrators, you can see them here, which surround the PMTs, which focus light onto the active area of the photocathode. Those have degraded, so you can sort of see it here, there's white patches on there that are not as reflective as they used to be. So again, we could just replace those. And those two together would win us a factor of 2 to 3 in light yield. The other option, if you contain the isotope in a bag, then you limit the volume it's in and you don't lose additional light outside that region. The other option is a new large-scale experiment. So that takes me into the last part of my talk, which is looking to the future, next generation projects and the development of new technology. So I mentioned that we need a couple of things to understand the matter-antimatter asymmetry in our universe. One is Majorana neutrinos, the other is CP violation. And there is a program in the US to search for CP violation using a liquid argon time projection chamber. This is the Dune experiment, which will be deployed at the Stanford Underground Research Facility, viewing a high-energy neutrino beam from Fermilab. So what I'm going to talk about is not this experiment, it's actually a complementary experiment which we hope to deploy in the same facility to do similar physics. So in order to understand the new technology, let's just revisit briefly scintillation and Cherenkov detectors. So remember, the scintillation detectors give you very high light yield, that means good energy resolution and low thresholds. It's isotropic light and it's particle dependent, so you can differentiate alphas from betas. Cherenkov light is directional. It's got this cone-like topology, and that allows you to do ring imaging, and you can identify, you can discriminate between electrons and muons, for example, by ring imaging. And in a water detector, you have very low attenuation. So you have high light collection. You may retain your photons. So what we would like to do is to leverage a tried and tested methodology, the idea of putting a large, a light-producing target inside a large monolithic detector, but in combination with novel cutting-edge technology. And that technology is this new target medium developed at Brookhaven called water-based liquid scintillator. And the idea is this could give you the benefits of scintillation detectors and Cherenkov detectors in a single experiment. So this is, it's really a very simple idea. You take oil and water and you mix them. Fortunately, we work with chemists who are quite clever and they know how to do that. And the result gives you really a very powerful target medium because you can tune it to meet your physics goals. Anywhere between the long attenuation lengths of water and the very high light yield of scintillator. This water-based scintillator can have a mix of oil and water anywhere in that regime. So what are the potential capabilities? Well, you can use the Cherenkov topology, which gives you directional information and particle ID at high energy. The fact that you've got water in there also means you can load metals. So you can load isotopes that are hydrophilic in nature. And you maintain high light collection because of the high transparency. But the introduction of scintillator means you have an increased light yield, which improves your energy resolution and lowers your thresholds. And even better, the whole is greater than the sum of the parts. By a comparison of the Cherenkov and scintillation signals, you actually get an additional handle on particle ID. So the experiment thus envisioned is the Thea Experiment. It's a realization of what we call the advanced scintillation detector concept. The idea is a large detector filled with 50 to 100 kilotons of water-based scintillator, surrounded with fast, high-efficiency photon detectors with high coverage. This detector would be deep underground, for example, at the Sanford Underground Research Facility, that's Homestake. And one of the critical things about this detector design is that it is flexible. It is flexible in the exact choice of water-based scintillator target, exactly how much scintillator you have in that cocktail. It's flexible in what isotope you might load into your target. And it's even flexible in the exact detector configuration. So for example, you could deploy a bag which would allow you to have a higher scintillator fraction in a confined region, or just to load isotope in a confined region, allowing you to potentially optimize for multiple physics goals at once. So to give you the scale, this just a monument with which presumably you're familiar. This is roughly the size of Snow Plus. Thea would be roughly this size. So the idea is this technology allows us to build large, directional, low threshold detectors. And that opens up an incredibly broad physics program. So I won't go through each of these in detail. I'm just going to throw up this list to mention some of the physics topics this detector could address. And what's interesting is that it covers topics canonically considered both high energy physics and nuclear physics. And I mean, potentially astrophysics, some of these as well. So that allows you to leverage experience and expertise from different communities. A fun fact is that this would be physics across 5 orders of magnitude in energy in a single detector. And a little bit of a brain teaser. The same detector could show that neutrinos and antineutrinos are the same by observing neutrinoless double beta decay, and that neutrinos and antineutrinos behave differently by observing CP violation. And those are the 2 critical ingredients to resolving the matter-antimatter asymmetry. So you could do that in a single detector. So let me just conclude with a few words on the ongoing R&D. There's a lot of very interesting questions to address, ranging from the properties of the target material itself, optimizing that cocktail for maximum physics output, how well you can actually reconstruct events in that target, and how good your timing has to be to do this Cherenkov scintillation separation. So this is really an extensive and very exciting R&D program. I'm just going to flash up this slide, which has some examples of the ongoing R&D. So there's the actual target development at Brookhaven. There's a lot of work in isotope loading. This is the same picture I showed before because this is a technology that we can use for loading into SNO+. Materials compatibility, purification, and then also photon detection, so both PMT development and other methods for photon detection, and containment technology. I've talked about the advantages of a bag. Now, of course, one of the really, the linchpin of this idea is that you can separate the Cherenkov and the scintillation light, and therefore have the benefits of both. So this figure in the top right shows you the time profile for the prompt Cherenkov and the delayed scintillation. So if you want to do this separation, you either need ultra-fast photon detectors, which are being developed. You can potentially just delay the scintillation light. That's an option in the water-based scintillator cocktail with various additives. Or you can optimize your cocktail. You can change the relative magnitudes of the two signals to improve detection. You can also play with your readout sensitivity. So this shows the emitted spectrum from scintillation light in red and Cherenkov in blue. This black dashed line here is sort of the standard efficiency of a PMT. If you move to a red sensitive PMT, which is this one here, then you become sensitive to that high wavelength tail of Cherenkov light above the scintillation spectrum. And these figures just show you the impact of the fast timing. So this is the timing of sort of a standard PMT with looking at pure scintillator. So the red is the scintillation and black is Cherenkov. You can see it's lost underneath the scintillation. But if you have very fast timing, 100 picosecond, you actually get a clear Cherenkov peak at the beginning. And there are PMTs with this timing, but there's also new photon detection technology. So to give you an idea what this might look like in the full detector, I hope you can see this okay. This is simulating 3 NeV electrons in a 5% water-based scintillator mixture, so that's 5% scintillator and 95% water. And the red, these are the scintillation photons, and the blue is the Cherenkov. So you can see that there's a cone-like topology. At the low energy, you get quite a lot of scattering, so that smears out your Cherenkov a little bit, but if you zoom in, you can actually see that there is a very clear cone here. And then if you go to high energy, so 1 GeV, which is where you would be looking for the beam physics, the long baseline physics, this is imaging just 1% of the photons, and you see you get this beautiful isotropic scintillation flash and this very clear Cherenkov cone. And if you image all the photons, you get something, this sort of Eye of Sauron-like effect. So you see you have very clear ring imaging capability in this mixture. So let me just show you a little bit of what we're actually doing here at Berkeley in this program. We have a cosmic muon ring imaging experiment. There's 2 parts to it. There's a timing measurement and there's a light yield measurement. So the timing uses small, fast PMTs, and the light yield measurement uses these large 10-inch photomultiplier tubes. The project is called CHESS, for Cherenkov scintillation separation. And this is just a close-up of the timing portion. So we have this grid of small, fast PMTs. They're these Hamamatsu PMTs with about 300 picosecond transit time spread. They're very nice. And this is what the setup looks like. So this is the PMTs here. This is a target filled with water-based scintillator. This is just a block of UVT acrylic for optical photon propagation. And then here and here, we have muon tags. They're just chunks of scintillator with PMTs attached to them, so that we can select vertical going cosmic muons, which will produce light in our target, and we want to image the Cherenkov ring. So the reason for the name, well, you can see the acronym, but also we think the board looks a little bit like a chessboard. So what you might expect to see here, this is a simulation for pure scintillator. Again, red is scintillation photons and blue is Cherenkov. So you can see that you do get a ring of Cherenkov photons. Now in pure scintillator, it's very difficult to distinguish even with good timing because you've got so much scintillation light. But this gives you an idea of what we might be able to do. So this is data that we've taken just with water. This shows you the timing response of the setup. We do get a width of about 100 picoseconds, which is really quite impressive. And then this is simulation. We don't yet have the data for the scintillator. It's running at the moment. But you can see if you simulate the pure scintillator, this is what we predict for the Cherenkov peak, and this is the scintillation light. So you see you do have some separation here, even in the pure scintillator. And what we want to understand is how this separation depends on the water-based scintillator cocktail itself. So there's a lot of ongoing R&D. We're not the only ones doing it, all around the country, all around the world, really. This is just a table that shows you some of the different projects that are contributing to this larger program. And this is a visual version that gives you a similar idea. There's all of these different aspects of R&D that are feeding into the development of this larger scale detector. So Thea's not a formal collaboration, it's a loosely affiliated interest group. This is just to give you an idea of those involved. It's based in the US, but with active involvement from Germany and the UK at the moment. And we are open to new collaboration if anyone is interested. So to conclude, neutrinos have really a long history of exciting physics and technological developments. The SNO+ experiment, which is coming online in the very near future, has the potential to discover the nature of the neutrino, which would go a long way to resolving the matter-antimatter asymmetry. And the future Thea detector has a really broad program of compelling science. It's a unique opportunity to combine conventional neutrino physics with rare event searches in a single detector. And what I think is really one of the critical sort of take-home points, it has the flexibility to adapt in new directions. So these large-scale projects, which take a decade or more to realize, during that time, the scientific field is going to evolve. You need a detector that can evolve along with it. So that, I think, really makes it a powerful instrument of discovery. And you've seen Thea travel around the world, so I thought I would bring her home to roost. So she's about 2/3 of the height of the company that we have. So thank you very much.
Very lucid and very efficient and very fast-moving talk here. My own favorite quotation of Wolfgang Pauli, apparently when the news hit Europe about the discovery of the neutrino after 20 years, Pauli and his gang apparently retreated up to the Alps for a nice party. And of course, high altitudes and champagne interact in a delightful way. And at the end of the evening, when everyone was cheery and tipsy, he was being helped down the mountain on the shoulders of a couple of his guardian angels there. And he turned to one of them and said, "All good things come to the patient." So anyway, those of us who do crazy things looking for accidents and so forth. Questions?
Yeah, can the neutrino escape a black hole? It's got mass.
No.
Okay.
No more than anything else should be able to.
I guess the black holes are too far away to look.
Well, yes, we haven't looked.
Okay.
It would seem to me that with such a high tellurium isotopic concentration, it would be easy to enrich the tellurium concentration. And if you're worried about getting enough of that isotope, you could do just a few stages of enrichment. You can get from 30% to like 8%, and then you drop your total metal concentration quite a bit.
So you certainly can enrich. We know how to enrich tellurium. It's not cheap. So our baseline, we actually have a number of potential paths for the future. We could right now, so actually let me just flip back for comparison. Let me put up the sensitivities. So this is the figure that shows the potential, the phase space. So the goal for next generation experiments is to get to below this inverted hierarchy region. So with SNO+, we know how to do that today. And the way to do it is to upgrade the PMTs to load as much isotope as we can enriched. And all of that we know how to do. There's no further R&D required. It just costs money. And basically, between now and then, all the R&D we do saves us money for the same sensitivity. So if we can increase the loading, then we don't need the enrichment, and that saves a lot of money. So that's the baseline plan.
Al?
You had showed a slide in a new section, Fermilab shooting beam somewhere else. I happened to work at the Japan Atomic Energy Agency for a while, and then there was the T2K project going on there. What What's the difference between that project and this project?
So T to K can do similar physics, but the sensitivity is not quite as good. The beam energy is different, and critically, the baseline is different. So the 800 miles is really important. You need the really long baseline. Yeah.
Okay.
So T to K, in combination with the Nova experiment, which has recently started in the US, will be able to tell us, sort of give us a hint for the neutrino mass hierarchy, and depending on the CP, on the value of the CP violating phase, may be able to measure it. This project will be able to do both to 5 sigma. So it's basically the next generation of the same idea.
If the neutrino and the antineutrino aren't one and the same, do we have any idea what physics governs how simply by shifting reference frame it becomes its antiparticle, or is that something that...
So it's not so much necessarily that it becomes its antiparticle, but it's effectively, so the helicity flip, as it were, goes with, I forget exactly the power, but it's m/e to the 4, maybe. So with the mass of the neutrino, we don't know what it is, but we know it's tiny. At any kind of reasonable neutrino energy, you have a tiny, tiny fraction. So a really, really tiny probability that you would get neutrinos of the other helicity. So it's sort of the typical answer of, okay, we've detected neutrinos from various sources. Surely we would know if they were their own antiparticle, because some of them would have interacted like antineutrinos. Yes, but such a tiny fraction that we would never expect to have seen them.
That's great. So you showed us a simulation of what you expect in Snow Plus when you're doing a double beta exert. And when you're dealing with a detector with moderate resolution, and this little peak is sitting on the side of the background that's coming down like the side of the house, that seems to be a situation where very small erosion of performance could quickly wipe out the signal. What have you done to establish sort of the basis that you'll be able to hold the line on your performance there so the signal won't get wiped out? Have you done sort of moderate scale prototypes, or?
So we don't have a prototype as such, but what we've done is stability testing of the Scintillator cocktail, and we've got that over about 3 years at this point. And we also have a calibration system that will allow us to monitor this effectively day by day.
Right.
So we have a embedded light injection system. We can pair it with either lasers or LEDs depending on the wavelength and the intensity that we want. And it's got 92 injection points in the detector, so we can monitor the scintillator properties very carefully.
Okay. Joe?
Following on the helicity state, so is lepton number conservation still enforced in beta decay, for instance?
So it is in beta decay. The thing that doesn't conserve lepton number is neutrino oscillation. But that's the only place that we've seen the
So if
violation
you had
to
a
date.
neutrino that beta decay is an antineutrino and from helicity, it becomes its own. Well, so how does that add up to 0 on the right hand side?
Well, right. So if
Oh, okay, I see.
yeah, in the helicity flip case, then you would have violation. But everything that we've seen to date concerns it, other than neutrino oscillation.
So going back to his question, do you manage to cover the inverted hierarchy region without being overwhelmed by the 2 neutrino tail,
Yeah.
given
So
the percentage resolution?
yeah. So we're actually above. In order to keep that background down, we need at least 200 hits per MeV of deposited particle energy. At the moment, so for our 0.5% loading, we're at about 475. So we can load quite a lot more isotope before we hit that issue. I actually don't think I have it as a backup slide, but I can talk it. So if you look at sort of half-life sensitivity as a function of tellurium loading, then the shape looks sort of something like this, where it's just starting to turn over at 0.9%. So we're loading 0.5, that's funding constraint, basically. So if we go to 0.9, without doing any changes to the detector, that's our peak sensitivity. If we then enrich, that's almost the equivalent of 3%. And that's what gets you to the bottom of the inverted hierarchy, with the upgrade to the peak as well.
Wonderful. Let's thank our speaker.